So what is number representation? Number representation is the system we use to represent unique values. If we have 10 apples, we would write that as 1 0 using a number representation system called decimal, also known as base 10. So what does decimal, or base 10, actually mean? What are bases? The term base refers to the number of unique digits, including 0, that a number system uses to represent values. In base 10, we represent 10 unique values using 0 through 9. And once we hit 10, we have to start over again and add an extra character. So why do we need to know about different bases for computer architecture? Well, computers operate by turning off and on switches called transistors, with high voltage representing a 1 or on, and low voltage representing a 0 or off. To understand computer operations and build the logic circuits to perform them, you need to know how to do math with numbers in base 2, or binary. With 1 bit, we can represent 2 numbers, 0 and 1. With 2 bits, we can represent 4 unique numbers, 0 through 3. By adding a new bit, we double the amount of possible combinations. Given this pattern, we can define an equation to represent the maximum magnitude given a number of bits, which we define as 2 to the n minus 1. If we have 4 bits, we can represent 2 to the 4 minus 1, which is 15. If we are given the 4-bit value 1111, 4 ones, we add 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. Which is 1 plus 2 plus 4 plus 8 is equal to 15. In addition to binary, another important number representation for computers is hexadecimal, or base 16, which is used to shorten binary numbers and is commonly used for memory addressing and color codes. Base 16 means there are 16 unique symbols for each place value. But how can we represent 0 through 15 using only one place value? Well, 1 through 9 are as you'd expect, but when we get to 10, we start assigning alphabet characters. So 10 through 15 are A through F. So we end up with 0 through 9, and then A through F to end up with 16 unique values. If we have the hexadecimal value A, we know A converts to the value 10. So we multiply 10 by 16 to the power of its index, or in this case, 16 to the 0. If we have the value 2a in hex, we take 10 times 16 to the 0 like before, but then we add 2 times 16 to the 1. So add 10 plus 32, and our final value of 2a is 42. Now that we know about different base systems, like binary and hexadecimal, how do we convert from decimal to different base systems? If we have a big number in decimal, like 2,576, how do we find out its binary value without using a calculator or through trial and error? We can use something called the shift method. The shift method involves repeated division by a base and concatenating the remainder value into our result. Let's start by converting a small decimal number, like 25, into a binary value using the shift method. So if we divide 25 by 2, our result is 12 with a remainder of 1. We then take that quotient 12 and divide it by 2 again, and we get 6 with a remainder of 0. We then divide 6 by 2 to get 3 and a remainder of 0. 3 divided by 2 is 1 with a remainder of 1. And 1 divided by 2 is 0 with a remainder of 1. Now that our quotient is 0, we exit the division loop and write out our remainders from bottom up, left to right in our resulting binary string. Our result comes out to 11001, an unsigned binary, or 25. If we wanted to convert from decimal to hexadecimal, we would follow the same shift method, but we'd be dividing by 16 instead of base 2. Given the same number as an example, 25, 25 divided by 16 is equal to 1, remainder 9. 1 divided by 16 is equal to 0, remainder 1. We hit 0, so now we write from the bottom up, left to right, and we end up with a result of 19 in hexadecimal. There is a shortcut to easily convert between binary and any other base that is a power of 2, 4, 8, 16, 32, and so on, called the power rule. If we're converting from binary to another base that's a power of 2, all we have to do is split up the binary into sections and then convert each of those sections to their corresponding base value. Hexadecimal uses one place value to represent 16 unique values. It takes 4 place values in binary to represent 16 unique values, so each hex value directly corresponds with 4 binary values. If I wanted to convert from base 2 to base 6, I wouldn't be able to do that because 6 is not a power of 2, or in other words, you can't take 2 to the x with whole numbers and get 6. In order to convert from binary to base 6, or hexadecimal to base 6, you should convert to decimal first, and then use the shift method to find its base 6 value. But what if we wanted to represent a negative number in binary or perform subtraction? Well, we could try a couple different approaches. One approach is to use what's called a sign bit, where we sacrifice the leading bit to use as a flag to represent that the following number is negative. But this comes with issues when adding a negative to a positive number, or in other words, performing subtraction. Using the leading bit, or sign bit, to represent a positive or a negative number is a common theme in every representation of negative numbers in binary, but we need to fix the subtraction problem with the signed approach. To fix the subtraction problem with the signed approach, we use what's called 1's complement, which means that we still use the sign bit, but if we want to take the negative of a number, we need to flip all of its bits. For example, if we have 0011 as 3, if we wanted negative 3, we would flip all the bits to be 1100. If we add 0011 plus 1100, we get 1111. So 1111 should be 0 because we added negative 3 and positive 3. So why is it 1111? Well, there are actually 2 versions of 0 in 1's complement, a positive 0 and a negative 0. 2's complement fixes both the subtraction problem and the 2 versions of 0 problem. If we're given the value 3, 0011, and we wanted to find negative 3 using 2's complement, we take the 1's complement and flip the bits to get 1100, and then we add 1 to get 1101. If we add 0011 and 1101, we get 10000. But we drop the 1 because our answer is in 4 bits, therefore we're left with 0000. If you need to find the real value of a negative number in 2's complement, there are 2 ways to do it. The more difficult, but still pretty easy method, is to make the last bit a negative and then just add the values of the remaining bits. For example, if we have the value 1110, the leading bit is 1, so we write negative 8 plus 4 plus 2 is equal to negative 2. The second method that I prefer for its simplicity is just taking the 2's complement of the negative number, and whatever that value is, it must be the negative value. So if we have 1110 again, we take its 2's complement, we flip the bits and get 0001, we add 1 and we get 0010, which is equal to 2. So we know our value must be negative 2.